This is video 2 from the GCSE Physics video series. This one's all about thermal energy transfers and energy transfers by heating, that sort of thing. We're going to have a look at the most common way that we talk about energy transfer by heating, that is conductive energy transfer by heating, conduction. And here's a diagram on the bottom right to show you what's going on. So on the bottom right, you can see we've got some sort of bar of matter. It could be a metal bar, copper, steel, something like that. Or it could be glass rod or anything like that. But we've got this bar that goes across here. And one side is held over a flame, so it's at a higher temperature. The other side is held in a hand. And energy is going to travel from the side that's at a higher temperature to the side that's at a lower temperature. And that is going to have energy travel in this direction due to conduction. So what does that mean? Well, that means that on the hotter side, the higher temperature side, which is indicated with this flame here, this is the high temperature side, the particles are vibrating around more than they are on the colder side, which is indicated with this block of ice over here on the right. Now, because of that, the particles on the left are going to knock into the particles on the right, causing the particles on the right to move more. The body's at a higher temperature if the particles are shaking around more. Now, I'm going to keep it vague like that at the moment. When we go into things like gas laws in A-level, we go into a lot more detail about what we mean by temperature, but for now, that's okay. Understanding that at a higher temperature, the particles that make up the substance shake around more. And I use the word particles instead of molecules. I prefer that word. You'll hear people talk about molecules. That's fine. It's not incorrect. So these particles are going to shake around more if they're at a higher temperature, causing them to collide into the particles next to them, transferring energy along. Fine. That is conduction. So what can we do to improve the conduction of a material? Or should I say, what can we do to improve the rate that energy is transferred from one side to the other side of a material? Well, we could choose a material that has a higher conductivity. Different media have different conductivities. Now, thermal conductivity is quite a complicated topic. There's a little box down here which tells you about thermal conductivity, which is given the letter K in this equation. This equation has a symbol which is an upside down triangle. That's the Greek, I don't know if it's Greek or not actually. It's the letter 𝗟𝗶, or sometimes it's called del. I don't think it is Greek actually. But this upside down triangle is complicated. It's a sort of three-dimensional gradient. So this is the temperature gradient. And that can be quite difficult to understand what that means. And the Q here is the rate of transfer of energy by heating. It's an energy transfer rate, an amount of energy that is transferred per unit area per amount of time, or a power per unit area. Now, you don't need this equation for your GCSE. You really don't. But it tells us some things that you do need to know for your GCSE. It tells us, for example, that if I have a higher difference in temperature between this side and this side, between the left and the right of our bar, then energy is going to be transferred across that bar by conduction at a higher rate. Okay, we take this equation, we rearrange it. K is some quantity to do with the material. You can't change that. And 𝗟𝗶 is the temperature gradient. So in 1D, it's just the difference in temperature divided by the distance along this bar. So multiply those two together. That gives you the rate of energy transfer by heating per unit area, Q. So that's telling us that if I have a bigger temperature difference, I have a bigger rate that energy is going to flow through this bar by conduction. Well, that's true, and you do need to know that. The higher the temperature difference, the greater the rate of energy transfer. But what else affects the rate of energy transfer? Well, you can see from this equation that K is proportional to Q. So if I have a material, a medium, a substance that has a higher conductivity, then we'll get a greater rate of energy transfer by conduction through that medium. It will conduct better, has a higher thermal conductivity, so that makes sense. Also, if we have the same difference in temperature on each side of the bar, but the bar is shorter, that will also increase the rate of energy transfer. Why is that? Because that's also going to increase the temperature gradient by decreasing the distance over which the temperature changes. So those three things, all three of those, higher temperature difference, greater conductivity, and thinner material, all three of those are going to increase the rate that energy is conducted through this bar. So if we want to reduce the rate that energy is conducted, we want to insulate our bar, or whatever it is, we want to insulate so that the energy stays in one place as much as we can, rather than conducting away. Then what do? We would do the opposite. We have a lower temperature difference from one side of the medium to the other. We have a lower thermal conductivity, and one of the lowest thermal conductivities is air, trapped air. And then we have a thicker material. So we have a thicker material with air trapped inside it. Because the air is trapped, that's actually going to reduce the temperature difference across the material. It's going to make it a more gradual change in temperature difference. Then that's going to reduce the rate of conduction. And that's what insulation has. So this is the sort of insulation you might have in a loft or in a cavity wall. This is fibers with air trapped inside them. Air has a low thermal conductivity. The thicker the insulation, the better the insulator is. Okay, so if we were doing an experiment to investigate thermal insulation, there are three things there that affect the insulating properties. That is the difference in temperature from one side to the other. So if this side of the insulating material was a higher temperature and this side was a lower temperature, energy is going to flow through the material in this direction. Let's label this hot and this cold. If the temperature difference between the hot and the cold is greater, we're going to get a greater rate of energy transfer. We're also going to have the effect of the material itself and the effect of the thickness of the material. So if we want to do an experiment to investigate insulation, we've got to be clear in our head, what are we investigating? If it's the type of insulator, the material it's made out of, then we need to make sure we keep the thickness of the insulator the same and the difference in temperature between the hot and the cold side the same. So that the only independent variable we have is what the insulator is made out of. If we were investigating the effect of thickness of insulator, then we'd have to have the same type of insulator, and again, the same difference in temperature across the insulator. What we're saying here is we need to make sure we've only got one independent variable, which is another way of saying a fair test. That's a pretty standard thing that we have to do in all science experiments. And I'm emphasizing that point because this is a required practical at GCSE, investigating insulators. Now, metals are better conductors or worse insulators than non-metals. And copper is a particularly good conductor, which is why the cooling systems within computers use things like copper heat pipes. Copper is a better conductor. Why is that? Well, there's also free electrons that can move around and travel through this material, carrying energy with them. Now, all the way through this, I've referred to energy being transferred by conduction. But sometimes you'll see resources that talk about heat being conducted. And I'll trip up and I'll say heat is conducted, and I'll say heat is moved as well. And that's okay. I'm trying to be careful not to say that because it's a little bit vague. The word heat, we usually take it to mean energy. But because we're not talking about moving the energy store, physically, mechanically moving the energy store from one place to another, That is what happens in the process of convection, but that's not included on the AQA GCSE. Other GCSEs do include convection, which is where a warmer fluid becomes less dense, floats above the cooler fluid, which is more dense. So the physical movement of a warmer fluid carries that thermal energy store, physically moves it. What we're talking about here is different. We're talking about transferring energy from one place, from one part of the substance to a different part of the substance. Or if we've got two different substances touching, from one to the other. So heating as a verb would be the transfer of energy from one thermal energy store to a different thermal energy store. Or from the thermal energy store in one substance or one part of a material to the thermal energy store in a different substance or a different part of the material. And that's what we usually mean when we say heating as a verb. So heat as a noun, a type of energy. We don't talk about types of energy anymore. We talked about that in the last video. So do be a bit careful with this language. I try to say energy transfer rather than heat transfer. And it's important to get the clear distinction between temperature and energy. Whereas if you use the word heat, it can get a little bit confusing for people. So I think that helps reduce the confusion. Right, let's move on to 2.2. So this is lesson 11. This is lesson 11 in the series now. Last one was lesson 10. That's how numbers work. We've just looked at thermal conduction. That's transferring energy by conduction, conductive heating. This would be radiative heating. This is radiation as a mechanism for transferring energy from the thermal energy store of one body to the thermal energy store of another. Now, radiation is, when we talk about infrared radiation, we're talking about part of the electromagnetic spectrum. So this diagram we can see on the top right shows the electromagnetic spectrum ordered from left to right in terms of frequency, with radio waves being the lowest frequency and gamma rays being the highest frequency. And right in the middle here, we've got visible light. This is the part of the electromagnetic spectrum that we can see. Now, the electromagnetic spectrum, some people will have done it in Key Stage 3, some people will not have done it in Key Stage 3. It comes up again in a later video, and we'll do it properly then. Again, it's the house of cards thing I mentioned last video. We're building up our idea of physics, but we've got to hold all our ideas of physics together very lightly in order to construct our house of cards. We can't take a single card and examine it in ridiculously detailed depth, place it down, and then take a second card, because the first card will just fall over. So we're going to have to take each of our ideas of physics and build them up bit by bit. If you've never heard of the electromagnetic spectrum before, you've probably heard of radio waves, you've probably heard of X-rays, you've probably heard of microwaves and visible light. These terms you probably have some familiarity with, but you might not know that they lie along a spectrum. What we're saying is the nature of visible light as an electromagnetic wave, an oscillation in electric field. Again, electric fields you may have done in Key Stage 3, you may not have done, but we will do it as part of your GCSE. Hold it lightly. Electromagnetic waves are oscillations in electric and magnetic fields. That's all they are. And if they oscillate at a certain frequency, our eyes are able to detect that. And if they oscillate at higher frequencies, well, we can't detect that with our eyes, but we can detect that with other things. So X-ray machines that we use in hospitals will detect X-rays. And we have gamma cameras and things in hospitals as well. If the shaking of the particles is at a lower frequency, the shaking of the electric field is at a lower frequency, then we might have microwaves, radio waves, and we've got maybe an aerial or an antenna in our car, or we've seen a police car drive past with a big aerial, and it's transmitting radio waves, and that's how it's communicating with police HQ. So we understand that there is something that's being transmitted through space carrying energy with it. Infrared radiation is part of that spectrum. And the part that we're concerned with is this part here. Okay, not the right-hand side, as it's drawn, that what we would call near infrared, which is near red, near visible red. We're talking about the bit a bit farther away. All bodies at temperature above negative 273.15 degrees Celsius, all bodies emit infrared radiation. They just do. They just do. Now, we can't actually get bodies to that temperature or colder. We just can't. It's impossible to get bodies down that cold. And by bodies, we just mean objects. That's what we mean in physics by bodies. So when I say all bodies with temperatures above negative 273.15 degrees Celsius, that is the coldest possible temperature in the universe, and no body can actually be at that temperature. It's too cold. Therefore, what we're saying is all bodies in the universe emit infrared radiation. All of them do. This minimum temperature that the universe can possibly reach, by the way, we call absolute zero. Again, that comes up later in your GCSE. Now, as I increase the temperature of our body, we increase the amount of energy that is given out by that body. It may look like on this graph here that it is 0 watts per square meter of energy that's emitted when the temperature is, use the top scale, because you haven't done Kelvin yet, so use the top scale, negative 273.15. It's not actually 0, it's just very close to it. It's not actually 0, I mean, it would be 0 at negative 273.15, but we can't actually get to that. So this is above 0. But you'll notice that the higher the temperature of the body, the more energy is given out per second per square meter. So this thing labelled P is not a power, it's an intensity of electromagnetic radiation of the infrared part of the spectrum, which is given out, where W is watts per square meter, so that's joules per second per square meter. So the rate of emitting infrared radiation increases as the temperature increases, and it's a non-linear relationship. That means drawn on a graph, it's not a straight line, and not directly proportional. It's a non-linear relationship. All we can say is as one increases, the other increases. So body temperature is around here, boiling water is up here, and so on. Now, that's not the only thing that happens as we increase the temperature of a body. It's not just as we increase the temperature, it emits more infrared radiation. That is true, but something else happens as well. And to understand what else happens, we're going to take an ideal type of body called a black body. So a black body is an ideal body. They're not necessarily coloured black when you look at them, okay? So I'll give you an example. The sun is a very good example of what's close to being a black body. And there's no way you could say the sun was black. A black hole is pretty much a black body as well. And black holes, they are black. But the sun is not black, but it is a black body. So when we say black body, we're not using the colour black. If you could say black is a colour, it's the absence of all light, isn't it? But we're not saying black body because it's coloured black. You know, my mobile phone here is black. My t-shirt is black. They're not black bodies. When we say black body, we are looking at an ideal situation. A black body will absorb all radiation that's incident on it. It reflects nothing. It transmits nothing. It absorbs all radiation incident upon it. That's one of the properties of black bodies. That's not the only property of black bodies. Black bodies also radiate energy, and the spectrum of electromagnetic radiation that they radiate away energy, the spectrum only depends on the temperature of the body. Nothing else. So real bodies aren't black bodies because, for example, I painted my hut here white with white walls. When the walls were darker, they radiated more energy than the walls do now that they're lighter coloured. It's much cooler in here now because I've painted the walls a lighter colour. Even though the walls are in thermal contact with the outside, so the temperature of the walls is actually the same as it was before, they radiate less energy because of the colour of paint I've used. So a black body, the radiation that's emitted is purely due to temperature and isn't affected by things like what colour you've painted it, or what the surface texture is, or if there's any other clever things going on with the surface. So this graph at the bottom here shows what's called the black body spectrum. It is the spectrum of radiation emitted from a perfect black body. The sun is very, very close to that. So if we have a body which is at 3000 Kelvin, Kelvin is a unit of temperature, okay, let's say it's around about 3000 degrees Celsius. It's not, I know it's not. 3000 Kelvin is going to be 3000 subtract 273 in degrees Celsius. I'm not motivated enough to work out what that is. Maybe I should do, shouldn't I? 3000 subtract 273. Oh, I don't want to pause the video and get a calculator out. You do it. Put it in the comments. Read the comments. Someone will have worked out what that temperature is in degrees Celsius. That temperature, when a body is at that temperature, the radiation it emits follows this spectrum. So we can see we've got visible light here. This graph has been flipped compared to the one above. So we've got visible band here in the middle, and then we've got ultraviolet to the left and infrared to the right, rather than what we've got here. And that's because here we are increasing frequency from left to right and decreasing wavelength, whereas here we're increasing wavelength from left to right on the x-axis. You may have done the wave equation, c equals f lambda or v equals f lambda in key stage 3. Again, hold it lightly. If you've not done it, we'll be doing waves later on in this video series. It's always worth watching the video series twice so that you can pick up on the things the second time around. So what do we get? Well, if you look around that temperature, our peak wavelength, so the wavelength where we get the most radiation emitted, is not in the red section. It's just to the right of red. It's in the infrared section. This, on the y-axis, it says spatial radiance. It's a little bit complicated here, but you've got kilowatts and per square meter, which is very similar to our watts per square meter from this, but it's also per nanometer of wavelength and per steradian of solid angle. Don't worry about any of that. That's much more A-level stuff. All that stuff, that unit is a horrible unit. It just tells us how much radiation is being given off. That's all it tells us, how strong the radiation is, corrected for wavelength. So here we have a peak around the infrared. Now, if I increase the temperature of the body, so about 4000 Kelvin, you'll notice the peak is in the red part of the electromagnetic spectrum. So that body is going to be glowing, not just emitting infrared, but also emitting enough red light that is going to look red. It might even look slightly orangey or yellow, because there's a significant amount of yellow and orange light being emitted here as well. If I increase the temperature further to about 5000 Kelvin, you'll notice the peak wavelength has shifted right to the middle of the visible spectrum, and we've got significant amounts of blue as well. That's going to start looking, around 6000 Kelvin, it's going to look pretty convincingly white. It's going to look like a white object. It's a black body, but it will look white. That's what's going on with the sun. If we can continue to increase the temperature of that body, that peak would continue to decrease in wavelength, and we would end up having a body which has the peak wavelength in the blue part of the spectrum, and it will look blue. And that's what we've got going on in this little animation here, and the one beneath it. What we're showing here, and it's all normalized, so the curve doesn't shoot up in terms of intensity the way it does in reality. You know, the graph is increasing intensity the whole time. We've normalized our curve so that doesn't happen. We're only interested in the perceived color, not the perceived brightness. we've got 3 receptors in our eyes, and we'll cover those again in more detail later. Small, medium, and large cones, 3 receptors that are sensitive to colour. There are other receptors in the eyes. There are rods, for example, that are not sensitive to colour and are much more sensitive to low-intensity light, but we're not talking about those. They're sensitive to bands of wavelengths. And as our temperature of our star or body, whatever it is, let's take a star, increases, you'll see that the peak wavelength shifts towards the blue part of the spectrum. And our blue receptors detect that and show the object as blue. So what we're saying is that blue objects, blue stars, an object that is radiating blue light as part of the black body spectrum, is at a higher temperature than something, a body that's radiating red light. So stars like Sirius are much higher temperature than stars like Betelgeuse, where Betelgeuse is a red star. And this graph down here is trying to show the same thing. The number at the bottom, I believe, is a normalization factor, but I can't remember. But this is showing temperature in Kelvin and the colour the body would appear to be according to the black body spectrum. So the experiments were done by Herschel. I think it was William Herschel. Someone will correct me in the comments if I'm wrong. You take visible light from the sun, sunlight, pass it through a slit, pass it through a prism, and you get a spectrum. So you can see we've got this labelled red, orange, yellow, green, blue, indigo and violet. Yuck. Purple. And if we place thermometers where the different colours are, we discover that the thermometer shows an increase in temperature when it's beyond the visible spectrum. More modern apparatus might look like this, with an electromagnetic radiation detector placed here, a piece of card with a slit in it, and you illuminate it with light from the sun that's been passed through a prism, and you'll discover a significant amount of radiation in the part where there's no light. That is infrared radiation. Now we can detect that with infrared devices like this very simple one, or more sophisticated infrared devices that are able to take thermographs like this, thermographs like this one. This has got a false colour, so that where it is red or even white, there's a much more infrared radiation reaching the camera from that particular place. Where it is blue or black, there's much less. And you'll notice that this building has pretty good loft insulation, but there's a lot of radiation escaping through the windows. But more interesting than that, if you look at the structure, you can see these green lines. So this might be an American building where they build them out of wood or something, and you've got those various stud walls, and where the walls are, there's less insulation there because there's wood there holding the structure together, and that's going to be conducting more energy through. And so the walls end up at higher temperature, so they emit more radiation. Now we do have to be careful here because, as I said, different surfaces don't behave like black bodies. Surfaces have what's called an emissivity. That is, two bodies at the same temperature but with different colours will emit different amounts of infrared radiation. Standard experiment you do with this is using Leslie's cube. It is a required practical at GCSE level, where you measure the radiation coming off different coloured surfaces which are at the same temperature. So when you use these thermal photographs, these thermographs, you do have to be a bit careful to interpret it correctly. Look, the roof tiles and whatever they clad the walls with, they're probably going to be about the same emissivity, but the glass from the windows will be very different. Is it higher or lower? I don't know. I really don't know. I'd have to look that up. So that is lesson 11. Lesson 12. So topic 2, chapter 3, lesson 12. We can do more about infrared radiation. So we can use shiny surfaces to reflect infrared radiation, and that can be really useful. So here's a refugee. Don't know who it is. This image was taken from Wikipedia. It's used under Creative Commons license, like all the images in my stuff is. They're cold. In order to prevent them from radiating too much of their heat away so that they cool down too much and perhaps even suffer hypothermic shock, we're going to wrap them in a reflective blanket, a foil blanket, which reflects that infrared radiation they're emitted back so they can reabsorb it, preventing them from getting too cold. That's a similar sort of thing that happens with marathon runners. While they're running, the muscles are being used. While their muscles are working, there's respiration going on at a higher rate, so the muscles' temperature is going to increase, and the body responds by sweating, so that as the sweat evaporates off our skin, the skin temperature and the sweat remaining temperature drops. So to keep us cool while we're running, we would otherwise, our temperature would increase and increase and increase because we're transferring energy into the thermal energy stores of our muscles while we're running. So the sweating is to try to dissipate that energy as much as we can so that we maintain homeostasis, maintain our same body temperature. What happens when the marathon runner stops running? Well, they've still got sweat on them, they're still sweating, but their muscles are no longer respiring at the same rate. So they're no longer putting energy into the thermal energy store of their muscles at the same rate, but they're still cooling at the same rate because they've still got sweat on them. So the temperature of the body is going to drop. And for, real intensive races like marathons, the temperature of the body can drop too much and it can be dangerous. So you'll often see marathon runners, after they finish running, they wrap them in a foil blanket. You might think they want to cool off, but they don't want to cool off too much. I think that's the problem. So if we consider the Earth, not a person, not a refugee or a marathon runner or a homeless person or whatever, let us consider the whole Earth. In the whole Earth, the Earth has an atmosphere, the Moon doesn't. And the Moon and the Earth are on average the same distance from the Sun as for each other. So the Moon's the same distance from the Sun as the Earth is. Sometimes the Moon's slightly closer, sometimes the Moon's slightly farther away, because the Moon orbits the Earth. But both the Moon and the Earth are about the same distance from the Sun. So you'd think the surface temperatures of the Earth and the Moon would be about the same. But they're not. Now, why is that? Well, the Moon has no atmosphere. So the side of the Moon that's facing the Sun increases in temperature huge, hundreds of degrees higher than what we would comfortably survive in. And then at night time, on the Moon, so when the face of the Moon that's on the other side from where the Sun is, in the Moon's shadow, that side of the Moon, nighttime on the Moon, the temperature drops down to much lower temperatures, hundreds of degrees below 0 degrees Celsius. So the hundreds of degrees of fluctuation in temperature on the Moon. If that was the case on Earth, life could not have evolved. But we've got a much more stable temperature on the Earth. Much more, because we've got an atmosphere. And the atmosphere acts as a buffer. It absorbs infrared radiation from the Sun during the day, and then is emitting that all the time, including at night time, which helps keep us warm at night and helps prevent us getting too hot during the day. So that's what this bit in here is talking about. You can pause the video and read that if you want to. They've got this, you can watch this NASA video here. Everything NASA does is in the public domain. And here we've got 235 watts per square meter. That's the intensity of radiation arriving at the Earth. 235 joules per second per square meter of the Earth's surface. And what do we get? Well, ultimately, 195 plus 40, which is 235 watts per square meter, gets back out into space. So overall, the amount of energy that's being delivered to the Earth is the same as the amount of energy that's leaving the Earth. So the Earth's temperature should remain the same. Actually, that's not quite true because of the human impact on the Earth. The increase in the amount of greenhouse gas has caused this picture to be wrong. We are now radiating less energy back out than we are absorbing, which is why the temperature of the Earth on average is increasing year on year on year. Shouldn't be. It's us. We're destroying the planet. So you can follow this around if you like, but the Earth's atmosphere absorbs some of the radiation that's come directly from the Sun, which prevents the Earth's surface getting too hot during the daytime. And is emitting it in all directions all the time, including at night time, which prevents the Earth's surface getting too cold at night. So let's move on to the next one. Here it is, specific heat capacity. Finally, some equations. We can actually measure stuff. This is lesson number 13. Read something recently that said, oh, we want a physics education that isn't all about equations. It should be more interesting than that. And whilst there is something true to that, these videos aren't very good in a sense because we should be doing practicals. We should be doing practical work. Physics is a practical subject. You can't get away from the fact that to make a practical useful, you've got to reach for the maths. You've got to use equations. So here's an equation that you are in fact given in your GCSE. It might not be written in that form. Depends on your board. It might use a Q instead of an E. It might use a T instead of the Greek letter theta. That's the Greek letter theta there on the top right. It might not bother with the deltas, but this is the way I'd prefer to write it. Delta E equals mc delta theta. Now, if we rearrange that equation to make C the subject, it tells us, it makes a little bit more sense. We can unpick what this equation means. C is a material property called the specific heat capacity. Now, specific heat capacity gives you an indication of how much energy a body has to absorb to increase its temperature by a certain amount. So delta E is about an amount of energy transferred into the thermal energy store of the body. Okay, that's what delta E is. The change in the thermal energy store of the body. Delta theta is the change in temperature. I'm using theta because the unit I'm using for temperature is degrees Celsius. If I were using Kelvin, I would use a capital T for temperature instead. But we'll cover all that stuff when we do gas laws later on in the video series. M is the mass of the body. So the amount of energy that is transferred per kilogram per degree Celsius of change of temperature, that is what specific heat capacity is. What does that mean? Well, if we transfer a certain amount of energy into a body, if it has more mass, we get a lower temperature change. Makes sense. The energy is spread out further. If we transfer more energy, we get a bigger temperature change for a given mass and a given body, a given type of material, substance. That makes sense because this fraction has to be equal to C, which is a constant. So you can run around this equation and see how it all fits together. There is a required practical to measure the specific heat capacity of a substance. And so how can you do that? Well, there are ways of doing it. You wouldn't do it using the pictures on the right here, where we're using a flame, a Bunsen flame. That would be a bad idea because we wouldn't reliably know how much energy we've transferred using a Bunsen flame. So what could we do instead? Well, instead of using the Bunsen flame, we could use an electric heater. Now, that means we're going to have to use some equations from the electricity section. It's our house of cards again. We haven't covered electricity in our GCSE yet, but you should have done it during Key Stage 3. So when I talk about current and potential difference, you should have some idea of what these quantities mean. Current, the rate of flow of charge measured using an ammeter, and potential difference, amount of work done per unit of charge that moves through a component, measured using a voltmeter. Now, we don't know what these mean at this stage. Don't panic about it. We're just going to use them and we'll cover them in a later part of the video. But the amount of power, the energy per unit time, we did that before. Let's just scroll back a few lessons. Where is it? Scroll back a bit further. There it was. Right way back in lesson number 9, we had the equation for power on the top right. So this is electrical power. The electrical power, the amount of energy per unit time that is being transferred by the heater, is equal to the current that passes through the heater multiplied by the potential difference across the heater. If we timed how long the heater was turned on for, we could multiply that electric power by the time, and it would give us an amount of energy that we have transferred by the heater. That is the delta E in this equation. So our delta E is equal to the current through the heater multiplied by the potential difference across the heater multiplied by how long, the duration, that the heater has been turned on for. I times V times T, where I is the symbol we use for current. Fine. So if I insert that heater into a block of iron, brick, or into a beaker of olive oil, water, doesn't really matter. If I insert that heater into them and have a thermometer in them as well, then as my heater runs, and I've got my stopwatch running, I can calculate how much energy I've put in, and I can also measure the temperature of the block as I go along as well. And that is a required practical. So before I go into the method, this box up here just gives you a wordy definition of specific heat capacity, which is this equation worded like that. Perhaps I should have, but per unit temperature would be better at the bottom, but it doesn't matter. Given rate of transfer of energy, so for a given power, a less massive substance changes temperature more quickly. Less massive means it contains less mass. So we've talked about that already. That's the same thing as what's going on down here. Right, let's look at the practical then. What do? Well, we connect our heater to our circuit. We stick it into our block of whatever we're measuring, or our beaker of whatever liquid we're measuring the specific heat capacity for. And then we measure the potential difference across the heater using a voltmeter, the current through the heater using an ammeter. Now look at the recipe I'm using to write this method. I'm saying what the quantity is that's being measured, potential difference, current, and I'm saying what the instrument is that's making that measurement. Voltmeter, ammeter. Look here, temperature using the thermometer, using the instrument. That is a really good habit to get into. Don't say vague things like measure how hot it gets using a thermometer. No, the quantity that you are measuring is the temperature. So say measure the temperature using a thermometer. Very important. So anyway, we switch it all on, measure the potential difference using a voltmeter, measure the current using an ammeter, start the timer, every minute measure the temperature using a thermometer. And because we're doing that every minute, then we can multiply the total time the heater's been on by the current, by the potential difference to get the energy that has been transferred. Plot that on a graph against temperature, and you get a shape like this. And that's what it says to do is point number 4, point number 5. Now this is interesting, this graph, because if you look, energy transferred, the longer the heater's on for, the more energy is transferred. But at first, the temperature doesn't change. That's interesting. And at the end, the temperature, it looks like it wants to stop changing. It seems to want to level off and stop changing. That's interesting. So you do have to understand why both those things are happening. Well, for a start, if our heater is in the iron block here and the thermometer is next to it, it's going to take some time for the energy to conduct to where the thermometer is. So that explains the delay at the start of the graph. Takes some time for the heater temperature to increase, and it takes some time for the energy to conduct from the heater to the block where the thermometer is. What explains the end? Well, eventually we're going to be putting energy in at the same rate that energy is radiating out. Even if we encase these blocks in insulation, it's not perfect insulation, and eventually the block will be at a high enough temperature that energy is going to be radiating out of the block at the same rate that we are putting energy into the block with the heater. So when that happens, the temperature of the block doesn't change. We're in what's called thermal equilibrium. That's a power equilibrium. So what part of the graph we're interested in is the straight part. Now, if we look at the straight part of the graph, let's take it between these 2 points. If we were to measure the gradient of this straight part of the graph, use a ruler and so on and so on, if you were to measure the gradient, what you would get is a change in the amount of energy that there is in the thermal energy store of the block or liquid. So that is delta E, that's the energy that's been transferred into there, and the change in temperature. And so the gradient is going to be equal to the amount of energy that's been put into the thermal energy store of the block divided by the change in temperature. And if you look at this equation, there it is, delta E over delta theta. So all we need to do is take that gradient and divide it by the mass, that's what's down there, to get the specific heat capacity of the substance. That's how we do it. Now I'm just going to restart these animations just so you can see what's going on. Let's compare iron and brick. They're both heated at the same time, and you'll notice that the temperature of the brick is going up quicker, I think. Yes, quicker than the temperature of the iron. So that means the brick has a lower specific heat capacity than the iron, because the temperature is going up faster. Now let's compare olive oil and water. Well, if you compare olive oil... Where's my cursor gone? There it is. If you compare olive oil and water, get them both to start at 0. There we are. So increase the temperatures together. You'll notice that the olive oil temperature goes up faster than the water temperature. So the water has a higher specific heat capacity than the olive oil. The olive oil has a lower specific heat capacity than the water. But the water temperature stops increasing, and that's because of another thing that can happen, which is the water's boiling. Now, we'll cover state changes and boiling in a later video. It's not part of this video. Let's just clear out my ink, and let's move on to the last lesson of this video, the last lesson of this topic. So this is lesson number 14 in total, heating and insulating buildings. So here's that insulation we talked about before being used in the cavity of a building. Most buildings in the United Kingdom are built of this construction. Most domestic buildings, most houses are built with this construction, although increasingly common are sort of steel-framed buildings which are clad. But there's still loads of these sorts of buildings around where you've got brick on the outside. This is the outside wall on the right. Then a bit of a gap, then breeze block, because it's cheaper and they're bigger bricks, so they're easier to put together. And then a bit of a gap, and then they're on the inside. So in the winter, we would have hot air on this side and cold air out on that side. In the summer, it would be the other way around. But let's take it for winter for now. So energy is going to be transferred from the hot side to the cold side. And we know that we can reduce that rate of energy transfer by increasing the distance. It's a nice big thick wall, so that works. By reducing the conductivity, well, we've trapped air in the insulation because there's air trapped in the fibres, so that's a big tick. And by reducing the temperature change across that gap. So how do we reduce the temperature change? Well, these are the ways we can do it. Okay, so let's start with loft insulation. You just pack this stuff up in the loft, traps air, fine. Cavity wall insulation, that's fine. Double glazed windows, it's not a vacuum in between the panes. It's usually very dry air. If the air gets any moisture in it, the windows can go cloudy. You can fix it, but it is not ideal. So double glazed windows, even triple glazed windows, air is trapped and air is a bad conductor. Aluminium foil is an interesting one. You put aluminium foil here, so if you have a radiator where I've labelled it R, and you place aluminium foil, then the energy from the radiator is going to be reflected back into the room, rather than being absorbed by that side of the wall, which means this side of the wall on the left is not going to be as high a temperature as it would be without the aluminium foil. So that reduces the temperature difference from inside to outside, which is what I mentioned just before, which means less energy is going to transfer from inside to outside the home. And lastly, thicker bricks, lower thermal conductivity, all that sort of thing, which I think we've already talked about. So that is stopping energy leaving our home in the winter. However, no matter how much insulation we've got, some energy is going to be leaking out of our home. So we're going to have to put energy back into our home. And we can do that in a few ways. We can use the burning of fossil fuels in central heating systems, not ideal. We can use a wood-burning stove, perhaps, a wood-burning fireplace. That has other issues. Yes, the wood is renewable and carbon neutral, carbon zero, but is releasing particles into the atmosphere, which it's pollution. It can contribute to things like acid rain. It can also actually have the opposite effect, which is the particles in the atmosphere can absorb the sunlight which actually cools down the Earth underneath, but not in a good way, because it means the atmosphere gets hotter or something. I don't know, I'm not a climate scientist. If you are a climate scientist, get in the comments and let me know. We can use electric heaters, so maybe we use solar panels to generate our electricity. Maybe we use wind turbines or whatever. And rather than burning coal, burning oil in our boiler, or burning gas, burning oil in our boiler, or burning coal, burning wood in our fireplace, we could use electric heaters. If there's a power station on the other side of the national grid burning gas, then it's not really, well, it's a little bit better in terms of efficiency, but it's not great. But if we use electric heaters, we might have it connected to a renewable resource, which would be even better. And then that just uses this dual heating, that is a current transferring energy into the home, into the thermal energy store of the heater. My house has these solar heating systems. Very lucky when I moved in, there are solar panels on the roof where cold water's pumped into them and the sunlight warms the water up. So 6 to 8 months out of the year, I don't use anything to heat the water up. The sun does it for me. So that's cheaper for me because I don't have to pay for hot water for 6 to 8 months out of the year. But it's also better for the environment. So that's what my home's got. So that's getting energy into your home. The better insulation that you've got, the less fuel needs to be burned or whatever to maintain the temperature inside. Now, what about in the summer? In the summer, we are usually wanted to be cooler on the inside because it's hotter on the outside. And the energy is going to try to conduct into our home. Well, better insulation is going to help, yes. Some people do have air conditioning, which is, I think, part of the problem. You know, if you think, oh, because of global warming, it's getting hotter and hotter and hotter, it's becoming unbearable, so I'm going to fire up the air conditioning. That means you're burning more fossil fuels to power the air conditioning, which is exacerbating the global warming problem in the first place. It's not helping. Just turn your air conditioning off. Just deal with the heat. There are other things you can do. You can open windows strategically to get a breeze that flows through because of convection, which carries the warmer air away and keeps the inside of your home a little bit cooler as well. There are things you can do. But listen, if there's no method of transferring energy into the home in the winter or out of the home in the summer, if there isn't a mechanism, then eventually you're going to get the inside the same temperature as the outside. Not quite true because the warm air gets trapped. So we have the effect that happens in greenhouses, which is not the greenhouse effect. I didn't name it. You get that effect happens. So it's not quite true. But yeah, if you're going to get cold on the inside of your house, if there's no method for getting energy into the house in the winter, no matter how much insulation you've got. Right, we'll stop there. That was too long a video, but there we go. That was lesson where is it? Lesson 14. So lesson 15, starting on energy resources, is the next video. Sort of introduce myself at the end of the video. My name's Keith. I am a physics teacher, a qualified physics teacher with lots of experience and an examiner, an Isaac Physics Ambassador, you name it. I'm telling you all this because I'm trying to make you consider whether you want to do our online tuition, weekly tuition. Every week I do online tuition live during term times. It's interactive, not like this. This is a video. It's not like this. Students answer questions. They ask questions. I answer questions for them. I ask questions. They answer them. They use the chat feature in YouTube to communicate with me during the live stream. They can also use an interactive whiteboard that they can see and I can see to give me answers. But the other students can't see each other's boards, so there's some anonymity there, so they're not embarrassed if they're getting things wrong, which it shouldn't be anyway. But it flows really well. And they're good sessions. They're really useful sessions. And they're dirt cheap as well. So if you're interested in them, there's a QR code there. Go to my website, physicswithkeith.com. Have a look how to enroll on those sessions. Thank you for tuning in. Hopefully you will tune in for the next video on energy resources. Take care.